Alrighty, all right. So here's the last example for the week 2 and the energy methods. This is an example problem from Dr. Bob, and we want to determine the effective mass of a beam with a concentrated load at the center. All right, so first things, we could look up and find the this displacement on a beam. If I could, let's see, I'm going to cancel out of that and see if it'll let me. How come it won't let me go to this? I guess I could have to unfold my laptop thing. See, I have this Surface Studio laptop thing that can switch things around. The screen can fold down. Why won't it let me do this? I don't know. Let me go Alt-Tab. Alt-Tab. It seems to be angry about something. I'm sorry. Okay, there you go. All right, so you could use the deflections of just about from any book, but here is the deflection. This is from Beard Johnston. I think I might be closing out of this thing pretty soon because he's acting up. So here's the maximum deflection at the center, right? But here's also an expression for what the deflection looks like from 0 to the midspan. So if you want to find what the deflection is at any given point along the thing, this is the equation to use. It's only good for from 0 to 1/2 L. But then it's a mirror image, so that's fine. I also would look at Shigley right here and go to them. If you're a mechanical engineer, this is a book that you'll be using. You can see you get the same thing right here. So it would and equations that we would use. All right, so let me go back to this guy and back into presentation mode. And if I was a real obsessive compulsive person, which I've been accused of being, I would fix this, but I'm tired and I don't want to do it, so I'm not gonna. So we could say that the Y max that you have at the center is going to be F times L cubed over 48 EI. Should have had some of this in mechanics and materials. And from that you could take the F over Y, or del, so that you could get the stiffness is 48 EI over L cubed. We might need that later. Let me see. I'm going to make this distribution. I'm going to go. Bob didn't do this. Dr. Bob didn't do this. So this is Y as a function of X is written out as Fx over 48 EI times 4x squared minus 3L squared. And I decided, okay, so let's try to make the stuff on the left-hand side look a little bit like this maximum right here. So I'm going to leave off that x right there. So F, and I'm going to distribute that x back out through the thing, but I'm also going to try to get that L cubed in there. So I'm going to go L cubed divided by 48 EI right here, and I'll say that. And I also decided, yeah, this is also, by the way, this should be negative. So I'm going to make this negative too. So I'll make this negative and go 4 times x cubed, because I took that x and multiplied by there, and it's going to be divided by L cubed, right? Because I put that L cubed right there, and then we'll have a plus because we had that negative, and 3x over a single L. right? Because it had L squared before, but we put that L cubed in there. So what we say right here is that's going to be the same thing as saying y max times this distribution. And I'm going to flop them around, so I'll go 3x over L minus 4x cubed over L cubed. And the reason for this, right, so that's this distribution, that's the deflection right here. Let's say that the velocity of each one of these like individual little points, the velocity is distributed in the same way as the deflection is distributed. So that's the concept that we're using right here. So let's forget about so if we wanted to find what the velocity is at the point when, like say the velocity right here is the maximum, which is going to be the same velocity right here, then the velocity of the maximum, so like instead of, we could replace that with just velocity, and this would be like sometimes we'll call this a shape function. And it literally is called a shape function. What is the shape of the thing? Well, it's kind of like this. We're describing a distribution. So we could say that the kinetic energy of the beam is going to be equal to 1/2, right, the mass of the beam per length, right? So that's what each one of these little chunks right here, we're going to say we're going to have like a mass density per length kind of term in here. And it's going to be multiplied by the velocity, right, of each of these little points, which, by the way, this equation right up above is only for 1/2 of the beam, so here's going to be times 2 of the beam. And now we're going to do an integral and say that we're going to have, and there's a lot of bracketage right here coming up, y dot max, so that's the velocity at the center when it's at its maximum right there. And by the way, we should probably say this is what we're doing for we're trying to find the maximum kinetic energy. So here's the maximum at the middle, but it's going to be times the 3x over L minus 4x cubed over L cubed. And we have to make that squared. And then we have to do this by here, and this we're going to go 0 to L over 2. Did I get everything? I almost want to have another 2. I don't know if I need another bracket. I don't think I need another bracket. I think I put one on my notes for no apparent reason. All right, so Ted's not going to do this. I'm jumping steps, baby. And so what I end up finding, I could, but you can't sometimes just be nice to yourself. I'm going to be a little lazy. And I'm going to go 1/2. I left one of the 1/2s in there, but I end up finding a number, 0.4857. Oops, MB, mass of the beam, times y dot max, y dot squared max. All right, so remember that we want to go T max equals U max. So what we did is the value added things, and also replace y with big Y is magnitude, and y dot with big Y. I live right next to a big Y. Did I mention that? No reason to. And random color change. We stick this in here and go 1/2, and I'm going to call, by the way, I decided to call this big M, 1/2 y dot max squared, sure, plus 1/2 0.4857 MB y dot max squared equals to the 1/2 K In this case, K is 48 EI over L cubed times Y max, not a dot, squared. And one thing we notice, we have the 1/2 go away. We go ahead and we're going to lump some things together. Boom, plus 0.4857 MB. Now we have Y squared omega n squared equals to 48 EI L cubed times big O Y squared. These go away, and what we're left with is omega n is equal to 48 EI divided by L cubed. There's an L cubed somewhere. That's where the L cubed comes from. And times at big M plus 0.4857 MB. Boom. And that right there is our determine the, okay, so we a long way away we did find the effective mass. This is the effective mass of the beam. It adds about 50% of the beam's weight gets added to the mass that it's supporting and will influence what the natural frequency is, which makes pretty good sense. I think of it in these terms, all right? So this is not correct, but I don't care. I do care, sorry. I think of it as this part of the beam, this part of the mass of the beam, it's really kind of like being supported by these supports. It's only this like middle section of the beam right here that's really being an effective mass and contributing to the natural frequency. Not sure, you know, a lot of times I think of this and I put it, I almost used the word lumped twice. I lump it together with the idea of the lumped mass. Lumped mass approximation. And I think it's correct. I mean, I've heard this term all the time, many times, and there's certain lumped mass, dynamics software where they, that's the basis by which they run the thing. They do a lumped mass approximation for the thing, and yeah, what we're doing, we're lumping the mass. Some of the mass gets lumped into the thing that's causing the vibration. Some of the mass gets lumped over to the boundary conditions where because it doesn't do anything, it doesn't contribute to anything. So that is my I don't know, jargon-filled explanation for what this is. So let's stop making videos today because I'm tired of my own voice. Whee!